Hello everyone. In this video, we'll be explaining how mass transfer is involved in wastewater treatment. So, here is an outline of what we are going to cover. First of all, we'll be looking at the aim of the presentation, then the concept of mass transfer which it involves, its explanation, followed by how that concept is being applied to our aim, then some enhancements that can be incorporated in the current approach, followed by the outro. So, moving on to the aim, which is application of mass transfer in wastewater treatment. Now, let's see concepts of mass transfer involved in it. Okay, so the fundamental of wastewater treatment is based on the two film theory. Let's see it in some detail. This theory makes a few assumptions, the very first of which is the presence of equilibrium at the interface, which means that the phases are at equilibrium at the interface. Second one is the presence of layers in the vicinity of interface at its either side. And the theory states that the mass transfer between these two phases takes place via molecular diffusion. Here we can take a closer look at the concentration gradients where Cgi and Cli are concentration of respective phases at equilibrium, which is at interface, and Cg and Cl are the bulk concentrations. And from the picture we can see that interface is an imaginary axis that separates these two phases.
Now, coming to the topic, wastewater is contaminated. One way to purify it is to ozonate it, that is, pass a stream of ozone through it to purify it. This is known as ozonation. Now, let's study the diagram given. This diagram depicts a section of water over which we are going to study the mass transfer process on a very molecular level. Okay, so on both sides of the water section is the turbulent flow and ozone is being supplied to it. Due to this supplied ozone takes place the formation of the ozone gas layer, also known as film, which is followed by the liquid phase layer. Both of these layers are stagnant. The delta G and delta L are the width or thickness of ozone gas and the liquid layers respectively. As we can see in the picture that initially the liquid layer does not contain any ozone and the gas layer is rich in it. This gives rise to the mass transfer. So the mass transfer takes place via two diffusion layers which are shown as gas film and the liquid film. In the entire process, ozone encounters the maximum resistance and diffusion through the liquid layer and then diffuses through the liquid, thereby purifying the liquid. Now, let's take a look at its mathematical aspect, that is the factors affecting it. For the mass transfer taking place, its rate can be expressed as a product of coefficient of mass transfer and driving force for the mass transfer. And the driving force in this case is the concentration difference of ozone in the equilibrium with the gas phase, that is, which comes from the ozonation at interface, and the liquid phase, which comes in contaminated wastewater. And the concentration of ozone at equilibrium can be calculated via Henry's law.
We can extend this expression for calculating the rate of mass transfer per unit volume as per the notations shown. And now let us take a look at the enhancements that can be made to the existing model. The first option is via adding compounds that consume ozone quickly, because as these compounds consume ozone, then the concentration difference or the gradient will increase and therefore will result in increased mass transfer. As per the cited journal, the rate of mass transfer increases by a factor of 6 to 7 times when the concentration of humic substances is changed to 40 mg per liter. This fact can also be considered for increasing the mass transfer. Also, we can definitely increase mass transfer via increasing value of Kl, for which we will have to change temperature and pressure accordingly. And thank you very much for your time. This marks the end of our presentation.